So in this lesson, we're going to be talking about complex numbers or imaginary numbers. Just as a quick reminder, I equals the square root of -1. So let's practice simplifying some radicals so I don't have any negatives inside the radical. So when I'm multiplying or dividing inside a radical, we can split up each piece. So I have -1 times 4. That's the same thing as the square root of -1 times the square root of -4. You can only do this if I'm multiplying or dividing. I can't do it if I'm adding or subtracting. So what is the square root of -1? That is I, just like we see up here. And then what is the square root of 4? It is 2. And typically we put the whole number first, the real number first. So I have 2I is the simplified version of the square root of -4. What about the square root of -36? That's like saying -1 times 36. The square root of each of those pieces is I times 6. Okay, what about the square root of -27? Well, that's not a perfect square. Let's just look at some factors. I know that's 3 times 9, and 9 is 3 times 3. So I have a pair of 3s that can come out of the square root, and then I have 1 3 that's going to be left inside the square root. And then -1 times 27, I can pull that out. So I get 3I times the square root of 3. Okay, what about over here? So again, the negative is going to become this I, and then x to the 6, that is 6x is x times x times x times x times x times x. So I have 1 pair of x's, 2 pair, 3 pair. So that is going to equal x to the third power, because you have x times x times x times I from the negative. Okay, let's look over at the cube root. So for square roots, I was looking for pairs of numbers that multiply to 4 or 36. And here for cube root, look for 3 sets of numbers that multiply. So let's write the factors of 8 down. So I know that 8 is 2 times 4, and 4 is 2 times 2. So here I have 3 numbers that are being multiplied together that can come out of my radical. So the cube root of 8 equals 2. Okay, what about the cube root of -8? So we can do a couple ways. One, I can split it up. I can do -1 times the cube root of 8. So -1, what number can we multiply by itself 3 times to get -1? That is -1. So when we have the cube root of -1, we get -1, and then the cube root of 8 is 2, like we saw over here. So we get -1 times 2, or just a -2. So we only get imaginary numbers when it is the square root of -1. Anytime we have an odd radical power and you have a negative, the negative can just come out, which is pretty nifty. Okay, what about, let's take a look. So we did the cube root of 8 and -8. What if I did the square root of 8 and -8? So 8 is going to be 4 times 2, and 4 is 2 times 2. So I can bring out 1 pair of 2's, and I'm still going to have 1 2 that doesn't have a pair, so I can't come out of the square root. So I get 2 times the square root of 2. Now what if I have a -8? Well, because it's the square root, we have the square root of -1 times the square root of 8. Well, I figured out the square root of 8 over here was 2 radical 2, and the square root of -1 is I. So there you go. Okay, so let's talk about how we can simplify things with i's. So we know that I is the square root of -1. What about if I did I squared? So that's the square root of -1 times the square root of -1, or the square root of -1 squared. That equals just -1, because the square root and the square cancel each other out. Okay, what about if I have I to the third power? Well, we can write out the square root of -1 3 times, and that gives me square root of -1 times square root of -1 equals -1, and then the square root of -1 we know is I. So if I do I to the third power, that is the same as -I. Another way I can look at it is I know that I to the third power is I squared times I. And I already know that I squared is -1 from over here, so I get -1 times I, which gives you that same answer. I go to I to the 4th power. So that will be negative square root of -1. We do that 4 times. Okay. So square root of -1 times square root of -1 is 1. Is a -1, excuse me. And then square root of -1 times square root of -1 is -1. And -1 times -1 is a positive 1. Or I can look at it, I could do our I cubed. We have negative I, that's what I cubed is, times I. Well, I times I is -1. And then we have -1 times negative, which makes it a positive 1. So 2 different ways get the same answer. So writing out the square root of -1 can get cumbersome, especially if you do it for a lot. So we can let's start looking for some patterns as we do these next ones. For 5, 6, 7, and 8, I'm just going to take the answer before and times it by I. Because we know that I to the 5th is I to the 4th times I. So I to the 4th is 1 times I is just I. Now for I to the 6th power, I can take I to the 5th times I to get I to the 6th. We know that I to the 5th is I and times I. So I squared. Look, that's the same problem I end up with up here. Weird. Square root of -1 times square root of -1, which equals -1. Okay, weird. I have the same answer there. Huh. Wonder why. Oh my goodness. I also have the same answer for I and I to the 5th. Okay, what about I to the 7th? So that's the same as saying I to the 6th times I. I know that I to the 6th is -1. The -1 times I gives me -I. Okay, weird. I have the same answer again. Let's take a look over the next one. So then I have I to the 7 times I to get I to the 8th. I to the 7 is -I times I. So I times I is -1. Then times negative equals +1. Whoa, I get the same answer. What if I did I to the 9th? I to the 9th. We get +1 times I, which just equals I. Okay, weird. All of those are the same. So when we are doing I to the power, we are going to get one of 4 options. I, -1, -I, or +1. Those are the only 4 answers that you can get. So let's take a look at what patterns we notice. Well, I to the 4th, these ones are all multiples of 4. Anytime it's a multiple of 4, you're going to get 4 sets of square root of -1s, which we get the -1 and times -1, which is a positive 1. So anytime you have to the power that is divisible by 4, you're going to get 1. Anytime you get a power, let's take a look here. How do I describe this? I always look at it, so let's see, divisible by 4, and then we have the other 2 even ones, right? So you have an even number that's not divisible by 4, like 2 and 6. That's going to be -1. And then if you have a number that's like 1 bigger than a positive number plus 1, or 1 less than a multiple of 4, that's all an easier way of looking at it. If you have a number that is 1 less than a multiple of 4, like 4, 7, that's going to be -I. And over here, if you have a number that is, you can think of it as like 1 more than a multiple of 4. Or you could think of it as just keep adding 4. You have 1 plus 4 is 5, plus 4, the next one will be 9, then 13, etc. So let's see how we can simplify some of these ones. So I to the 50, that's an even number. Is 50 divisible by 4? No. So that means it's going to be like an I squared pattern. So this is going to equal -1. Or another way I could write it out is I'm now going to have I to the 25th squared. Is that helpful? Oh, here's another way of doing it. I have I squared to the 25th power. You know that I squared is -1, and -1 to the 25th power equals a -1. That's not a bad way of doing it. Okay, let's look at 81. So I can think of this as I squared. How many I squareds will I have? I'll have 40 I squareds, and then you times it by I. Okay, so I squared is -1. -1 to the 40th power will be a +1. Then you have 1 times I, or just I. Okay, I to the 100. So I have I squared. How many times do we have that? I have it 50 times. So I squared is -1 to the 50th power, which is going to equal a +1. Or you can say, oh, I know that 100 is divisible by 4, so that makes it just a +1. Okay, let's look over at 36 of I to the 36. So I have I squared. How many pairs of I squareds do I have? 18. So -1 to the 18th power will again be a +1. Okay, let's talk for a second about the fundamental theorem of algebra. So the fundamental theorem of algebra says is whatever the degree of our polynomial, that is how many solutions we will have. And that can be real solutions or imaginary solutions. So let's look at this problem right here. So I have an x squared graph. And do you remember x squareds have two solutions where your function equals 0. So we can say really easily here and here. Okay, well, what about over here on this graph, x squared plus 4? Here, let me write this down. Oh, sorry, I come back to this problem. So I have x squared minus 3x minus 4. So the degree is 2, so I should have two solutions. And we can see from our graph, those happen at x equals -1 and at x equals +4. But over here on my graph, I can't see it as easily where those solutions are. It doesn't quite make sense to me. Because I know it's a degree 2, so I should have two solutions, but it never crosses the x-axis. That's when you get imaginary solutions. So let's solve this. So I have x squared plus 4. I want to know where it equals 0. So I'm going to -4 on both sides. So I get x squared equals -4. Take the square root. X equals plus or minus. Now the square root of -4 is going to be I times 2. Talked about that earlier. Too many plus or minuses. There should be an equal sign. Equals plus or minus 2i. So see, I have the positive 2i and the negative 2i, and we still get two solutions. Sorry, Cami messed up the formatting. Oh, it should be on the next page. So look over here. We have x cubed minus x. We should get three solutions. And I see my solutions 1, 2, 3. Three solutions. We have them at x equals -1, 0, and 1. Okay. Go to this graph. So this is an x cubed graph also. Let me type the equation in here. This is x cubed plus 2x squared minus 3. Or I could say it's x minus 1 times x squared plus 3x plus 3. And so if I'm looking for my solutions, I'm like, where do each of these equal 0? Well, right here, where does x plus 1 equal 0? X minus 1 equals 0 when x is 1. So we can see one solution, but I don't see it cross the x-axis anywhere else. So I need to take my polynomial and solve. So our degree is 3. I have one solution, x equals 1. I need to find the other solution. And so we have this quadratic x squared plus 3x plus 3. X squared plus 3x plus 3. And a great way of finding imaginary solutions is with a quadratic formula. So I'm going to do negative b, which is 3, plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is 3, all over 2a, which is 1. 2 times 1. So we get, one second. So now let's simplify. So I have -3 plus or minus, so that's 9 minus 12. So that'll be the square root of -3 all over 2. So if I simplify this, I get -3 plus or minus I times the square root of 3 all over 2. So the plus is one answer, the minus is another answer. So I have 1, 2, 3 solutions. Now your imaginary solutions will always come in pairs because you always have the plus and the minus. So if you only have one imaginary solution, you know you did something wrong. You should always have pairs of imaginary solutions. So let's talk about why that is. So in conjugate pairs, the pairs of imaginary solutions are always called conjugates. And so here's what we mean by a conjugate. It means that I multiply them together, that the imaginary numbers cancel each other out. So our two imaginary solutions were negative 3 plus I squared of 3 over 2 and negative 3I minus negative 3 minus I squared of 3 over 2. So one reason they come in pairs is because when we multiply them out, we will cancel the I. See how in this equation x cubed plus 2x squared minus 3, and I see more specifically just the quadratic, we don't have any i's in there. That's because when you multiply the pairs together, the i's go away because I times I equals negative 1. So let's take a look here. Let's multiply those out. So negative 3 plus I squared of 3, and all of that is divided by 2, or times 1/2. And then times, again, I'm going to bring the 1/2 out just to make it a little easier to look at, minus I squared of 3. Okay, so if I do the 1/2 times the 1/2, that gives me 1/4. And now it's this part. I have negative 3 times negative 3, which is 9. Negative 3 times the negative I root 3. So the two negatives will make positive. Positive 3I squared of 3. Now let's do this next piece. I times the square root of 3 goes here. So that's going to be negative 3I square root of 3. And then times these two together, I times negative I will be, so I times I is negative 1, and then times a negative makes it positive 1, and then square root of 3 times square root of 3 is positive 3. So we end up with 1/4 times 9 and then plus 3I square root 3 and minus 3I square root of 3 cancel out, because if you have 3 and negative 3 or something, they go away. So I get 9 plus 3, which is 12, and 12 divided by 4 is 3, which is that like 3 at the end of your equation. Right there. So that's why imaginary numbers always come in pairs, so they can multiply out and they won't be in your final equation. So let's practice writing the conjugate pairs of each of these imaginary expressions. So if you have a positive I, the opposite of that will be negative I. Here we have 2 minus I, so the conjugate of this will be 2 plus I. You just change the sign in the middle. So here I have 7I. That conjugate is 7 minus I. Here I have negative 3 plus I. Then it'll be negative 3 minus I. The sign of the first number doesn't matter. It's only the sign of the second. So now let's multiply each of these together. So what is I times negative I? Well, we know I times I is negative 1, and then times negative 1 makes this a positive 1. Okay, so here I get 2 times 2 is 4. 2 times I is plus 2I. Negative I times 2 is minus 2I. And negative I times negative 1, negative I times positive I is a positive 1. So the 2 i's and then 2I and negative 2I cancel out, and we'll just get 4 plus 1, which is 5. I'm going to get the same pattern every time. Let's see, take a look. 7 times 7 is 49. Then I get minus 7I. Now here I get plus 7I. I times negative I will be a positive 1. So let's cancel out, and we're just left with 50. So I have negative 3 times negative 3, positive 9. Negative 3 times negative I is plus 3I. I times negative 3 is minus 3I. And I times negative I is plus 1. So those cancel out, and we're just left with 10. So if you multiply conjugate pairs together and they do not go away, the i's don't go away, then you need to go back and check your math, because they should multiply out. Okay, so instead of rationalizing the denominator, we want to realize the denominator, or make the denominator a real number. So to get rid of the I on the bottom, I'm going to times by I on the top and on the bottom. So I get 4I over I times I is negative 1. So we get negative 4I. Okay, what if I want to get rid of the i's on the bottom here? We times by 3 plus I. Times 3 plus I. Okay, so on the top I have 5 times 3 is 15 plus 5I. Then on the bottom, 3 times 3 is 9. 3 plus I plus 3I the negative I times 3 will be minus 3I, and the negative I times positive I is plus 1. So those cancel, and we get 9 plus 1 is 10. So 15 over 5I over 10. And if we want to simplify more, all of these are divisible by 5, so I can divide everything by 5. So that equals 3 plus I over 2. Okay, last try. Last practice. So I have 4 plus I. Let me choose a different color. So the conjugate pair of that is 4 minus I. Okay, now why am I timesing by the top and bottom of the fraction? Because I want to keep the fraction the same. And if I multiply by 1, like if I do 5 times 1, it still equals 5, right? So I'm going to times by 1. So the value doesn't change. Because if I have any number, like let's say I had like 2 divided by 2, anything divided by itself equals 1. So that's why I'm timesing by the same number on the top and on the bottom. So I get 4x minus ix over 4 times 4 is 16. 4 times negative I minus 4I. I times 4 plus 4I. It's plus sign. And then I times negative 1 is plus 1. So my i's cancel, and I have 4x minus ix all over 17. Okay, last part is doing operations with imaginary numbers. So we're going to practice simplifying the following expressions. So basically you have to combine like terms. The real numbers with the real numbers, imaginary numbers with imaginary numbers. So 3 plus 5 is 8. Negative I plus negative I would be, now I have negative 2i's. That's it. Here I have 3 minus I minus 5 minus 1. So make sure we distribute the negative to both pieces. 3 minus 5 is negative 2. And negative I minus a negative I minus a negative I. I want you to subtract 2 negatives. That is the same as adding. Those go away. And we just have negative 2. Now let's multiply. So 3 times 5 is 15. 3 times I is minus 3i because it's a negative I. Negative I times 5 is minus 5i. Negative I times negative I. Well, the negative and negative is positive, and then I times I is negative 1. So I have 15, and 15 minus 1 is 14, and the negative 3i minus 5i is minus 8i. Okay, what if they asked you to do like 3 plus I squared? It's tempting to just distribute across the addition sign, but you cannot do that. You can only distribute exponents across multiplication. So we have to write it all out. 3 plus I times 3 plus I. Now let's multiply each piece. 3 times 3 is 9. 3 times 3i is plus 3i. I times 3 is plus 3i again. And I times I is negative 1. So 9 and negative 1 combine to be 8. And 3i and 3i combine to be 6i. So I hope that gives you guys some help with the complex numbers, imaginary numbers. And if you need more help, come talk to your teacher. I'll be happy to help you.